Hi friends, this is Rishi and welcome to Science with Rishi. This is the video number 6 of the chapter Units and Measurement, Class 11 Physics. And today in this video, we are going to deal with the topic Dimensional Analysis. See, in this physical world, we have so many physical quantities, right? And some of them are basic or fundamental like length, mass and time, while some are derived from these ones, right? Like velocity, acceleration, force, volume, density, etc. So let's first consider these three, and among them the first, the length. The length you can measure in any unit, right, from millimeters to kilometers, right? But whatever be the nature of the unit, what are you actually measuring? It is the distance, right? So generally we can write length in this format, okay? Capital L within a square bracket. So that means whatever be the nature of your unit, you are measuring length, right? Similarly, how can we derive or how can we conclude it for mass? It can be from milligram to kilogram or even up to ton. But basically what we are measuring is mass. And similarly for time, it can be from millisecond to year or whatever it may be, but you are measuring the time. Now we can write these units in terms of this L, M and T. We know we can represent velocity also in so many ways, in meter per second or in kilometer per hour, or there are many other units. In all these cases, what actually velocity means? It is the distance by time, right? So we can write velocity as distance by time, or LT raised to minus 1. Understood? Similarly, acceleration, what is it? Velocity by time, LT raised to minus 1 by time, which is LT raised to minus 2. Similarly, if you consider force is mass into acceleration. So M LT raised to minus 2. What is volume? Volume is length into breadth into height, which means length into length into length, L cube. And what is density? Mass by volume, M L raised to minus 3. So here I have written all these units in their dimensional formula. Okay, so what is the dimensional formula of velocity? It is LT raised to minus 1, and for density it is ML raised to minus 3. You don't have to by heart all these things. You know what is velocity. It is length by time. So you can derive it. This is not a big rocket science. Just know the fundamental and just know what is their unit. You can easily derive all these things. And the only thing that you have to note is whatever be the unit, their dimensional formula will be same. And if you are taking velocity, whether it is initial velocity or final velocity or average velocity, or if it is the distance, total distance traveled, or the displacement, whatever it is, the dimensional formula will be always same. Now, what is the difference between a dimension, a dimensional formula and a dimensional equation? We all know the very famous and very simple equation, force is equal to mass into acceleration. Now, what is mass into acceleration? Kilogram into meter per second square, or M into L t raised to minus 2. So for force, mlt raised to minus 2 is its dimensional formula. Okay, mlt raised to minus 2 is the dimensional formula, and if I write in this manner, this is the dimensional equation. Okay, this part is the dimensional formula, and if I write F is equal to mlt raised to minus 2 in square bracket, this is the dimensional equation. Now, what is dimension? Dimension is the power of each and every basic quantities. Okay, here we can write m as m raised to 1, L as L raised to 1, and T is T raised to minus 2. So how we can say the force has got a dimension of, the mass of dimension 1, length of dimension 1, and time of dimension minus 2. What do you mean by homogeneity of equation? Homogeneity of equation is saying that you can add or subtract only same physical quantities, or if they are dimensionally same. For example, you can add time and time, but you cannot add time and distance, because time and distance are two different physical quantities, or dimensionally they are different. Now, if an equation is right, the dimensions on the left hand side and the right hand side of that equation will be same. Let's check it with an example. Okay, we all know the equation for the time period of a simple pendulum, t is equal to 2 pi root L by G. Now let's check this one dimensionally. This is time period. Okay, so t equal to 2 pi is a constant, and that has got no dimensions. L, length, divided by G. G is meter per second square, which is LT raised to minus 2. Right? LT raised to minus 2, their root, equal to, let's simplify it. This L and L will get cancelled, and root of t square, which is t. See, the dimensions on the right hand side matches with the dimensions of the left hand side, right? So we can say dimensionally this equation is correct. Now let's consider next example, another very familiar equation, S is equal to ut plus half at square. Let's check the dimensions on the right hand side. What is u? U is velocity, right? Velocity, meter per second, or L by T. L by T. T is time, so T plus half is a constant, we can neglect it. A is meter per second square, or L by T square. L by T square into T square. Now if we cancel T and T, and we cancel T square and T square, it is L plus L. And what is the dimension on the left hand side? This is distance, which is also L. So here also we can say that dimensionally this equation is correct. Now when we did the dimensional analysis of these two equations, and after we have found it is correct, I told you that yes, these two equations are dimensionally correct, and I didn't tell that okay, this equation is correct, right? Why I told you so? Because see, this 1 by 2 or this 2 pi, they are constants, right? And they don't have dimensions. If instead of this 1 by 2, if I write 100, okay, and instead of this 2 pi, just imagine I wrote 8 pi. Here also dimensionally this equation is correct, right? But the equation as such has gone wrong, right? So we have to conclude, or this is a rule, that if an equation is right, then dimensionally they will be right. But an equation that is dimensionally correct doesn't tell you that the equation is right. Okay, and this is the last sentence that has been written in bold letters before the example 2.15 in your textbook. Now the last topic of your chapter, deducing the relationship. This can be explained in the best manner with the example 2.17. In that example, they are saying that the time period of a simple pendulum is dependent upon the mass of the bob, the length of the pendulum, and the acceleration due to gravity. Okay, how to solve this? They are saying that the time is proportional to m, L and G, by which we can write time is equal to a constant into mass raised to x, length raised to y, and G raised to Z. Okay, now let's write it in dimensional method. T is equal to K into, okay, I'm sorry, there is no K because this is a constant. M raised to x, L raised to y, and what is G? LT raised to minus 2 raised to Z. Okay, T means M raised to 0, L raised to 0 and T raised to 1 equal to M raised to x, L raised to y plus Z and T raised to minus 2Z, right? Just expanding this RHS. Now just equate these two, where we will get x equal to 0, y plus z is equal to 0 and minus 2z equal to 1, which gives z is equal to minus 1 by 2, and substituting this z is equal to minus 1 by 2 here in the second one, we will get y is equal to 1 by 2 and x is 0. Now how to rewrite this one? T is equal to K into M raised to x. X is 0. So we can write M raised to 0 and L raised to y. Y is half and G raised to minus half, or T is equal to K into root of L by G. And for this equation, K is 2 pi and T is equal to 2 pi into root of L by G, which is the equation we saw just before, right? So hope you have understood how to deduce the relationship. And with this topic, we have come to the end of our chapter 2. In the next video, we will start with the next chapter. Until then, Rishi signing off. Bye. Take care. Jai Hind.